All right, welcome everybody. So in this lecture, we're going to be talking about molecular orbital theory for diatomic molecules specifically, okay? And we'll go beyond, obviously, just H2. All right, but first, let's just return back to H2, right? So just, again, last time we talked about how we can take a combination of this 1s orbital on hydrogen 1 and the 1s orbital on hydrogen 2 to form the bonding orbital and the anti-bonding orbitals, right? You have your bonding orbital, your anti-bonding orbital, right? And this diagram here is referred to, right, as an MO diagram, right? Molecular orbital diagram, MO diagram, right? And so sometimes we may not draw the things on the sides or whatever, but you know, this is referred to often as a molecular orbital diagram, right? These horizontal lines are representing the orbital energies, okay? So, right, so that's why, for example, the bonding orbital is at a lower position here than the non-bonding 1s orbitals or the anti-bonding orbitals, right? And that's, again, representing this at a lower energy. Okay, so these horizontal lines are energies, right? And then the arrows are your electrons, right? So these are your electrons, okay? Basically, what we'll be doing is we'll be generating these molecular orbital diagrams for diatomic systems, and then basically you just fill up from the lowest energy orbitals on up, first unpairing your electrons before pairing them up whenever possible, okay? Right, and so for example, as we talked about in the previous video, right, He2 doesn't exist because you would fill up 4 electrons in this MO diagram, and those 4 electrons, right, would occupy the bonding orbital here and occupy the anti-bonding orbital here, right, which that is going to have a higher energy than if you just left the electrons over by the atoms themselves and not considered putting them in bonding and anti-bonding orbitals, right? So again, this He2, right, would have this electron configuration, right? That's the electron configuration, right? And right, you would have these bonding versus anti-bonding orbitals being filled up for He2, and that would not be ideal, and this would never happen, and that's why you don't have He2 dimers that are covalently bonded to each other. Now, there are intermolecular forces, right? There's very, very weak attractive forces between heliums, and that's why you can get liquid helium and things like that, right? Just because things don't bond together doesn't mean that you can't form liquids and solids, right? They're just not covalently or ionically bonded to each other, right? That's what we're talking about here, is covalent bonds, ionic bonds, strong, right, sharing of electrons or transfer of electrons, right? It's not just intermolecular interactions like hydrogen bonding or dipole-dipole interactions or dispersion interactions, okay? Those are completely different things than what we're referring to here. All right. So when we talk about these different species, we'll often talk about bond order, okay? Bond order is given by the equation here, right? It is just 1/2 times the number of electrons in a bonding orbital, number of electrons in the anti-bonding orbital, okay? So the bond order for helium is 0, right? Which says helium's not going to be bonding at all, right? And so this bond order is a very useful kind of qualitative tool to kind of give us a sense of how strong 2 atoms might be bound together, right? And whether or not they are bonded at all. Okay, so for example, again, helium dimer has a bond order of 0, so that would be non-bonded, right? That wouldn't bind at all with each other. All right, so now let's look at beyond the first row of the periodic table, right? In the second row, talking about lithium and was it beryllium, I think, boron, carbon, nitrogen, oxygen, fluorine, and neon, right? That second row of our periodic table, okay? And so we're going to talk about mixtures of the 2s orbitals as well as the 2p orbitals, right? So we have, right, the 2s orbitals that will mix together and the 2p orbitals that will mix together, right? And we'll focus on those two things independently of each other, okay? And so for the 2s orbitals, those are going to mix in the same way as the 1s orbitals did, right? In the 2p orbitals, what we'll see is that we'll have one set of p orbitals that point together in the same direction of the bond, right? If I'm just talking about diatomic, right? The p orbitals, right? Or if I have just some atom, right? My p orbitals, right? Look. Actually, let's do a different color for each p orbital here, right? So I have 3 different p orbitals, okay, representing these different colors. You know, drawing this in 3 dimensions is a little tricky, right? But technically, there's this 3rd p orbital. Well, that's very difficult to see. Right. But let's use the purple here. Right. There's like 3 p orbitals, right, in 3-dimensional space pointed in different directions, right? If I have 2 atoms, right, one over here, right, then one set of those p orbitals, the green set, are pointed along each other, while this blue and purple set of orbitals are pointed kind of parallel to each other, but not towards each other. Okay, and so that's what it's kind of referring to, is that we'll see the p orbitals will be split into kind of 2 different ways of interacting based off of if they're directly pointed along each other or not. Okay, and here is showing pictorially what these orbitals end up looking like in terms of our bonding orbitals and our anti-bonding orbitals. So notice here that the bonding orbital has this Garrod symmetry like we had in the 1s orbitals, right? And the anti-bonding orbital is ungarrod, right? So again, this is bonding, this is anti-bonding, right? While for the p orbitals that are not pointed along each other, okay, we'll have, right, these will be referring to as our pi orbitals, right? And we see here that for the pi orbitals, this Garrod symmetry is actually our anti-bonding orbitals, and then this ungarrod symmetry is going to be our bonding orbitals, right? And it's because of kind of just the symmetry in how these orbitals overlap with each other, right? I want, as I invert between the center, right, I want to have this go from minus to plus, so that at the top side, right, I have plus and plus, right, so that I have some overlap between these orbitals up here and down here, right, on the top and bottom, right, and that's creating your pi bonding orbitals versus your sigma orbitals, right? So you see here, right, the overlap's not going to be as strong as the sigma orbitals, right? That's why your pi orbitals are weaker than your sigma orbitals. Okay, and so here I'm drawing out the MO diagram for your second row elements, except oxygen and fluorine, and we'll get to oxygen and fluorine in a minute. Okay, so here we have the MO diagrams for you know, the second row elements besides oxygen and fluorine, right? You have your sigma 1s orbitals, your 2s sigma orbitals, your pi orbitals, and your sigma orbitals, and pi antibonding and sigma antibonding orbitals. Okay, so there's a very common molecular orbital diagram for a diatomic species. Right? Often when we're drawing these molecular orbital diagrams, we'll just kind of ignore the orbitals down here. Think of those as more core orbitals, and we'll focus just on the valence orbitals up above, right? The 2s, 2p orbitals. Okay, so here in this chart, we have that same type of diagram kind of represented, where again, I have, so this 1 sigma, this is like my 2s orbital sigma bonding, and my 2s orbitals anti-bonding orbitals, okay? And these are the pi orbitals, this sigma g, right, pi g, right, so sigma bonding and pi bonding, or pi anti-bonding orbitals for your p electrons, right? So these are all for the p electrons here, right? P electrons, okay? And down here are your s electrons. Okay. And so one thing you'll notice is some trends that are occurring here. Okay. And so some of these trends are that as we go from left to right here, we see that these orbitals all lower in energy as we go from left to right. Okay, right? Every one of these orbitals decreases in energy as you go from left to right. Every one, right? And the reason for that is because if you go from left to right in the periodic table, if you remember from general chemistry, right, we're increasing the effective nuclear charge on these valence electrons. So basically, these electrons are feeling stronger attractions to the positive nucleus, right, as you go from left to right in the periodic table. That means this effective nuclear charge is increased. That means you're stabilizing these orbitals, right, because it has a stronger Coulomb attraction of the positive charges, which is lowering the energy. Okay, so this increase in effective nuclear charge is why all the orbitals go down in energy, right, as you go from left to right. We'll notice, though, that there's a big difference for the sigma bonding p orbitals here, right, where there's a large shift in energy, right, as you go from left to right, right, as you're increasing this effective nuclear charge, okay? And the reason for that is, again, you are increasing the effective nuclear charge, so that is lowering it, but also what's happening is, as you increase the effective nuclear charge, right, that decreases the effective size of the atoms, right, and the effective size of every atom is just really related to the average distance the electron is away from the nucleus, right? And so what's happening is these orbitals are all kind of being compressed closer and closer to the nucleus. And for the p bonding orbitals, you have this issue, right, that for the sigma p bonding orbitals, you have these lobes that are pointed directly at each other, okay? And when you're in something like lithium and beryllium and even boron and carbon and such, right, there's a lot of overlap between these orbitals, and it's actually kind of too much overlap, that you've crowded the electrons too much in the same region of space, and that's increased electron-electron repulsion within that space, and that's destabilized these orbitals, okay? And so that's why for lithium to nitrogen, the sigma bonding orbitals in the p space is in higher energy than the pi bonding orbitals. That's because of this electron-electron repulsion for this very, very, very high overlap in these orbitals, right? But once we get to things like oxygen and fluorine, okay, you've condensed these orbitals down and greatly reduced the overlap between them, and that's greatly reduced then this electron-electron repulsion and this kind of steric clouding, right? You have a lot of this kind of just things compressed in too small space, right, for these lithium to nitrogen, but for oxygen and fluorine, you shrunk the orbitals enough that now the electrons aren't overlapping with each other as much, and you have more room to breathe, if you will, right, and that's lowering the energy. And so that's why the sigma bonding orbitals in the p space decrease so much faster than all the other. And that is why you then get this unique case where for oxygen and fluorine, the p sigma orbitals are lower in energy than the pi orbitals, while for the other diatomic molecules, the pi orbitals are lower in energy than the sigma orbitals. Okay, and so we'll end this here for this video, and in the next video we'll kind of wrap up these homonuclear diatomics and do some examples and some questions and things like that. Okay.